Welcome, good evening. This is the Dawn and CosmoQuest Google Hangout that we've been advertising now for a little bit. And we're here in December. Turns out that Google has decided to call December Destember with STEM in the middle of it. STEM stands for Science, Technology, Engineering, and Mathematics. So they're giving a shout out to those particular professions. My name is Joe Wise. I'm the EPO manager for the NASA Dawn mission. You may know that the Dawn mission launched in 2007 with a trip out to the asteroid belt. We just finished orbiting Vesta, and we're now on our way to Ceres. And that orbiting of Vesta, we were able to bring back quite a few framing camera images, and those images have been collected and put up in a very interesting citizen science tool that we're calling Asteroid Mapper. And we hope that most of you are here this evening to participate in this hangout to learn about how to use Asteroid Mapper and some of the ways of identifying different surface features and such, so that you can help our scientists better understand this intriguing protoplanet. I'm here tonight with Dr. Pamela Gay, who is one of the creators of the Asteroid Mapper program, and she's at CosmoQuest. I'm also joined with Jennifer Scully, who is from UCLA. She's a grad student with Dr. Chris Russell, who is the principal investigator of the Dawn mission. She's also delivered a recent paper at the American Geological Union on the surface features of Vesta. Our producer this evening is Nicole Gulucci, and I would be remiss if I didn't also mention Nicole Hess, Judy Conley, and Whitney Cobb from McCrell in Denver, and also Scott, who was a major help in us pulling this together from CosmoQuest. So I know you're all anxious to get started with the talking about the asteroid mappers and how you can participate in helping the science team in understanding Vesta. And so I'm going to pass it off to Dr. Pamela Gay at CosmoQuest. Pamela, thanks for joining us.
So sorry, having mute button fail there. Thank you so much for helping us bring all of this together, Joe. It's been really an amazing over a year and a half that we've been working on building towards having Mercury mappers out there, asteroid mappers out there in the wild for people to be working on. Brittany Schmidt, who's currently in Antarctica, she and I started talking about this project back in March of 2011, and we finally got to start building this project last January. Jennifer's been there as part of the team selecting the images that would go out to the public, helping us figure out all of the technological issues, and today that software is out there. And I'm going to go ahead and bring it up. And Jennifer, could you explain to our audience what the scientific goals of this project are?
Yeah, sure. So, as you said, I'm a part of the science team working on the Dawn mission. And what we're looking for is something that can get members of the public involved in doing science that will be both beneficial for them and beneficial to the scientists. So we're getting people to help mark lots of features on the surface of Vesta. So then we produce a statistically and searchable catalog of all of these features that the scientists can go into and then analyze these features more in depth. So that basically everybody gets something out of this exercise, which is what we thought was really important.
So Asteroid Mappers is just one of the many different citizen science projects that we have at CosmoQuest, which is at cosmoquest.org. And to get to it, just go to our homepage, and it's linked right at the top. And you can just click Let's Explore. And it takes you in, gives you a pretty panorama of an artist's rendition of the area around Vesta with the mission in place. And when you first get started, it will take you through a tutorial. Now, I've been to this project before, so I get to skip the tutorial and take you straight in to look at this really amazing world. Now within CosmoQuest, we have Asteroid Mappers Vesta Edition, which gives us a small rocky body that in fact is so small that it's not spheroidal like the Moon and Earth and Mercury are. We also have Moon Mappers, which is looking at a bigger dry rock, or at least mostly dry. And then we have Mercury Mappers, which is looking at even a bigger world much closer to the Sun. And as we look at Vesta, we get to see, well, we sometimes refer to it as the world created by Dr. Seuss. Can you help our viewers understand why it is that Mercury has these strange cracks and rifts and shadowed features? And while you explain, I'm going to actually sit here and work on marking some craters.
Cool, sounds great. So as you said, there's all these craters on Vesta, and then there are also these groove features that you can see going diagonally across the image. There's an awful lot of craters, first of all, because, as you said, Vesta's in the asteroid belt, so there's an awful lot of other asteroids out there, and they just pummel into Vesta and make all of these craters over its history. Vesta's been around since pretty much the start of the solar system, and it doesn't have an atmosphere like the Earth to protect it from things coming in and impacting it, so you just get tons and tons of craters. And then you also get these linear features that we can see. And some of these are possibly formed by the regolith, which is the kind of sandy covering of Vesta, just being moved around by gravity, so it just cascades down and forms these kind of grooves. And also it's possible that some of them could be formed by small-scale tectonics. So tectonics possibly caused by impacts and things like that. So there's a number of different linear features that we get, and we also get boulders that I think you might be marking in a moment. So these are just larger bits of debris that come out of a crater after it's formed. They just get thrown out and land on the surface. So we have all these kind of interesting surface features. You can see there's a lot just in this one image. So when people are marking up these images, it's really helpful for the scientists, because it means that the scientists that we have don't have to go through all of the images in as much detail. If the citizen scientists can do that for us, that's great, because then we can move on and do the science on all of these features that are marked.
Now, for those of you who have any questions for us, we are doing this live. We would love to hear what all of you have to say. And the easiest way to get a hold of us is to go to the YouTube version of this, and that's the set of comments that most easily reach us. We know this video is getting shared out all across Google+. We are following it on the event page and on the Dawn page where it originated. When we see your questions, then we'll work on getting them up and answering them as best we can. Now, one of the things that I know I found kind of confusing looking at Vesta that maybe you can help us understand is we know that on the Moon we end up with boulders because essentially large asteroid, not as large as Vesta, but many meters to hundreds of meters size asteroid comes along, careens into the Moon, digs into the bedrock, throws boulders all over the place, and in the process of throwing the boulders creates secondary craters, boulder fields, all sorts of crazy stuff. Now, how is it on a world as small as Vesta that we don't end up with these boulders getting sent into orbit around Vesta?
Yeah, as you said, the Vesta's small, so you're going to have less gravity than the Moon and everything like that. But basically, the whole process just scales down. So you are going to lose some of the boulders just out into space, but then some of them that are the appropriate size with respect to the gravity of Vesta will stay on the surface. It's also possible that they might get thrown farther away than they would on the Moon because the gravity on Vesta is less, but you still get a reasonable amount of boulders accumulated. And when you're doing the mapping, sometimes when you're starting up, it can be hard to tell whether you're marking a crater or you're marking a boulder because they're a similar shape. But as you can see, when Pamela's doing the mapping, we have this nice little sun symbol on the right-hand side of the image. So this tells you which way the sun direction is coming from in the image. So from this, you can look at the shadows, and then you can tell whether a feature is a depression like a crater or sticking up like a boulder. So once you keep track of where that sun symbol is, it's relatively easy to tell the difference between the two.
And one of the things that we know frustrates people is there's all these little craters that you may want to meet and mark, and I'm like trying to mark this one, but when I mark its edges, I'm getting this red crater, and I let go and it goes away. So we're actually only marking the fairly large craters, and it's kind of amazing all the different types of craters. And in this case, we're looking at a really neat slope where you can actually see the material that's fanned down some sort of a slope. What are all the different types of geological surfaces that people might run into as they explore Vesta?
Well, this image that you've got up is a good example. As you said, we have material flowing down the sides of the crater, and then also towards the center of this image, we have quite a smooth area. So it's possible that some of these smooth areas could be something like impact melt, or they might just be very fine-grained material that gives a very, very smooth surface. Also in this image, you have there's a small, large peak in the center of this crater. It's just to the right of all the boulders that you've marked. So we get larger features like that are bigger than your general kind of boulder. And then also this image shows some of the Vesta's pitted terrain. This is mostly above and to the left of the boulders that you marked. And these pits aren't formed by craters. And this is because they don't have a rim around them like a normal crater. And they also kind of merge together, which is something that craters don't tend to do. So because this is very similar to pitted terrain on Mars, the Dawn scientists are thinking that this is formed by volatile material escaping after it was heated by the impact that formed the crater. So we have this sort of material in a few craters on Vesta. It's not that common. So most of the time, if you do see a depression, it's going to be a crater, but occasionally we have this pitted terrain.
Now, when scientists start talking about things like volatiles escaping, and I know I'm completely guilty of this, we're suddenly speaking in a secret language, and so I know that Vesta is this atmosphereless, like little tiny squished blob with wrinkles around its outer edges. When we say volatiles, this means this little world has gases, ices, things that want to escape, trapped inside of it. What's the origin of all of these different gases and ices that want to escape?
Yeah, well, that's something that we're looking into the moment. An easy way to get this to Vesta is from impacts of things such as comets and things like that. So that material gets deposited on the surface, maybe buried, or possibly it just impacts and then vaporizes away, forming this kind of pitted terrain. But we're also looking into the possibility that that material could be in Vesta for a really long time, possibly since nearly after it was formed. But it's probably kind of a mixture of both, possibly. There's a lot of different sources.
So we have a question coming in from YouTube. Jonathan Langsdale asks, how can you tell the velocity and size of an object that may have impacted, he says Moon, I'm going to say Vesta as well. Do the size of craters mean faster or larger impact? And that's a really interesting question.
Yeah, definitely. So certainly for the size of the object, a number of people have worked out equations that tells you the rough size of the object compared to the size of the crater that you get on the surface. It's a little bit complicated because you form a crater right after impact and then this collapses a little bit more over time. But generally, it'll be a number of fractions smaller than the size of the crater, the impactor that formed it. And then also for the velocity, on Vesta, impacts are going to be slower than they are, for example, on the Earth. And this is because, like we mentioned earlier, Vesta has a low gravity, so it's not going to pull things in as quickly.
So I just accidentally flashed the next question I was going to ask. Before we get to that, one thing to make clear to people is when rocks from space hit other rocks in space, the Earth being a particularly large rock, the reason that we always get round craters is all of the energy of the impact, both the velocity of the motion and all of the energy that comes from just being either really big or really small gets released. So all of this kinetic energy, the mass and the velocity combined, gets released and it radiates outwards, melting a chunk of whatever it hit in the process. And so when we see these craters, they aren't formed by something hitting straight in. In fact, they can be created perfectly round even from something coming in at just 10 degrees angle to the surface. It's this energy of the release. And this means that you can have both a moderately sized super fast moving object or a fairly large but slower moving object to create similar craters on the surface. So there's lots of really neat physics involved, and if you've ever studied the damage that can be done by guns, there's actually a grad student group in Europe that builds simulated asteroid surfaces and then shoots things at it to see what it takes to destroy the surface of asteroids. And I think that's just a kind of awesome thing to get to do as a grad student.
That sounds fun.
So Ken Daniell, sorry for what I just did to your name, asks, how can scientists tell that samples found on Earth are from Vesta specifically? We hear about, Brittany's down in Antarctica, scientists returning from Antarctica with meteorites that they think are Vesta class. How do they figure that out?
So the meteorites that are thought to come from Vesta, they're called the HED meteorites. And we think that they're from Vesta. It's pretty clear now that they're from Vesta because, first of all, before the Dawn mission got to Vesta, people could look at the spectra of Vesta through a telescope. And then also when they got these meteorites, you can shine a light on them in the lab and look at the spectra, and these matched very closely. So people thought that it was very likely that these meteorites came from Vesta. And since Dawn has gone to Vesta, we've got a really good confirmation of this because we have our spectrometer instrument and the framing camera and also our gamma ray neutron detector, and that's told us that the composition of the surface of Vesta is pretty much exactly the same as these HED meteorites.
And so what's kind of awesome is you guys are really kind of the CSI of planetary science, where with CSI you have them doing mass spec of this and that to determine what the paint composition is. Well, you're using the exact same technology that we see in this TV show to say, hey, this chunk of rock someone brought back from Antarctica is made of the same stuff that, well, reflected light indicates Vesta is made of. And the nice thing is, this means that we have samples of Vesta without having to send a spacecraft there. Just like we actually have samples of Mars and other objects in our solar system. And this is kind of weird to think about, but there's also probably samples of Earth on Mars. And this is because sometimes when we have these giant impacts, those boulders that get thrown up, they do actually escape. And sometimes they're just small meteorites, and there are able to travel the distances between worlds and eventually get caught up in the gravity of, well, Earth, or, well, Mars may have consumed a few bits of Earth over the years. And this allows us to sample these other planets. Now, it doesn't give us what's called ground truth information. This is where you look at the surface, you get a rock from the surface, and you compare the two. Apollo allowed us to do this with the moon, and we can only hope someday to be able to do this with asteroids as well. Now, Corey Terschmidt is making the comment, this is new to me. Why are you enlisting the assistance of the public, and what benefits does mapping an asteroid provide?
Okay, well, first of all, enlisting the public is really, really helpful for us because while we have a reasonably large science team, we have nothing as large as the whole of the public. So when we get people to help us by marking up these images, we get a very comprehensive catalog of all of the features that are on Vesta. And it would take the scientists that we have a very long time to do this, but if we can get a number of people on the CosmoQuest website to do this, then it means that we have this catalog that we can go back to, and we can then analyze the distribution of these features and how they formed and everything like that. So we can spend a lot of time doing all that kind of science and producing really high quality science without having to spend a long, long time marking all these features up. And then the reason that we went to Vesta in the first place was because it is believed to be very, very old. It comes from just the first few million years of the beginning of the solar system. And because it has no atmosphere, it hasn't been modified as much as the Earth was by atmospheric and water processes and plate tectonics. So it's kind of like a fossil of the early solar system. So the Earth itself was probably built by things like Vesta colliding and sticking together and then getting bigger and bigger. But this one just never formed a planet. So it's kind of like having a fossil of the early solar system. So that's why we were interested, and that's why we went.
And one of the things that has to be pointed out is we can't do science anymore without enlisting the public. It used to be that missions just didn't have that much hard drive space, is the best way to look at it. Now they usually use tape or other forms of magnetic drives. But 50 years ago, when Mariner 2 flew past Venus, this was the first time we actually sent back data to Earth of another planet using a space probe. And Mariner 2 could only hold 6,000 characters of information. Now, if you think about how much you might tweet in a given day, 6,000 characters suddenly doesn't seem that much. So we're now at the point where we have missions like Solar Dynamic Orbiter, which are returning hundreds of gigabytes of data every single day. As we made that transition from a page's worth of characters to an entire laptop's worth of information every single day, it got to the point that we couldn't analyze the data that was coming back by ourselves. And there's just not enough students out there that if we enlisted every single planetary student in America doing nothing but mapping rocky worlds, they still wouldn't be able to make a dent in it, which is fine because we don't need too many students because there aren't too many jobs, which is a different problem. But by engaging the public, all of you out in the public, all of us as small children, I think it's fair to say, we either wanted to dig up dinosaurs or study planets and stars. Well, the asteroids killed the dinosaurs, we win, and now you have your chance to study asteroids. And so come help us do the things that we can't do alone. Help us fully utilize the capacities of this amazing mission that's out there. So what got you involved in working on this, Jennifer?
Well, I applied to a number of different universities for my to do my PhD, and then I got an offer from UCLA saying would I like to work with Professor Russell, and it would be on the Dawn mission. So I joined just about a year before Dawn got to Vesta, so I got to get to grips with the mission and getting to know everybody and know about Vesta, and then I just kind of dived right in and got involved with doing all the geology stuff. So on a day-to-day basis, I map the surface of Vesta. Unfortunately, I can't use Asteroid Mappers because it's a really, really nice interface.
Well, I actually have good information. We're actually about to launch a scientists-only mirror version of the site that will allow people like you to come in, say which images you want to look at. You can mark everything using our interface, and that way you can more easily compare your results to the public. So this is something that we hope to have out by January 1, so you will get your scientific wish. This is something that our moon people, our moon leads, Irene Antonenko and Stuart Robbins, have been asking for the past several months. And over Christmas, we're moving to version 3 of our website software, and you're going to get your ability to use our shiny tools.
Great, that sounds great.
So if you want to send us a message over Twitter, if you use the hashtag Asteroid Mappers, I can suck it in and display it like I've been doing with other things. But I do see that we have a tweet from Ulysses, forgive me, and he's asking, given the current financial situation, is there a way to get private industry into exploring or exploiting asteroids? Do you know anything about what the commercial programs are working on?
I don't know too much about it myself, but I know people are interested in asteroids possibly for mining them or something like that. So I certainly think it would be great to go to asteroids and get to explore. So I'd be happy to tag along on a mission like that. But I think we're a while off anything like that.
That's kind of awesome. I'm scrolling through. I saw a couple great questions, and then everything went phew. Thanks for all your great questions. So here's a good one from Ken Denali, whose name I'm going to repeatedly mispronounce and I'm going to repeatedly apologize for. Why would Vesta have a composition that's so unique from that of other asteroids that you can tell from its spectra? What makes it so unique and easy to distinguish?
Well, we have a number of different kinds of asteroids out there, and because Vesta is basically just a basalt on the outside. It's kind of like a little mini Earth. It has an iron core, and then it has a mantle made of olivine like we do. And then the outside is a specific kind of basalt called a eucrite. And our oceanic crust is also made of basalt like that. A lot of the other asteroids...
And basalt is a fancy word for rock that got melted and then hardened back up.
It's basically lava that comes out on the Earth on like Hawaii or anything like that. So it's a pretty common throughout the solar system. A lot of the asteroids that are out there are ones that didn't get melted, so they have different spectra. So it's kind of just, there are other asteroids that have a similar spectra to Vesta because they're also covered in basalt because they were melted. But you get kind of small differences in the type of basalt that you have, and then the spectra just looks slightly different. And when you study it for a living, you get pretty good at telling them apart.
So another question that we have coming in from someone who's clearly used Asteroid Mappers. So thank you so much for going out and using it. I unfortunately don't have attribution for this one. Is coming in from one of the other people who's helping me monitor all of the questions. When you're using Asteroid Mappers, sometimes you're going along and you see giant craters, and sometimes you're going along and you see little tiny ones. Are all the images actually the same scale size, or are we seeing images with different zooms?
No, they're all the same size images. These aren't the size of the images that we got down from the spacecraft. We cropped them up into smaller images. But they're all the same width and the same height. I can't remember exactly what it was in meters. I know it was 450 pixels by 450 pixels. But I can't remember what that translates to in meters. I don't know if you remember, Pamela.
No, I'm afraid I don't.
Yeah. But it's a reasonably small scale that we're seeing. Yeah.
And so nothing is degraded image-wise. We're showing you the images at the fullest resolution that they came back from the mission. So it's you're not losing any detail. And when you see these different variations in size, what you're actually seeing is sometimes Vesta gets hit with small things, and sometimes it gets hit with large things, and these create different geological surfaces. And that's just the reality of it. So we have another question coming in from the forums. The person writes, it's obvious from the images that we're getting views of the same surface from varying altitudes and sun angles. Does this help with the surface interpretation or the building of a detailed map?
Yes, certainly. That's something that that was designed into the image. We had a number of different heights that we orbited Vesta at. So we started farther out and then moved closer in, and then we had a close approach, and then gradually as we were leaving Vesta, we moved back out. So the different altitudes gives you higher resolution or lower resolution images. So when we were at a very low altitude, we could see very fine scale features. And this is great for the fine scale interpretation. And then when we're at a higher altitude, you see more the kind of broad scale of what's going on. So when you can combine this all into your maps, it's very, very helpful for doing the interpretation. And then also the angle of the sun is important as well, because sometimes it can be hard to tell exactly the kind of shape that a feature has. So if you can see it when the sun is shining from another angle, then you get a more fuller picture of what it actually looks like.
And one of the other neat things that I've picked up looking at things from different angles is when the sun is straight overhead, it makes it really easy to see differences in the actual color of the soils, to make out rays and ejecta blankets and places where things got melted and flowed across the surface. But it's harder when the sun is straight overhead to see the edges of craters and boulders disappear almost entirely. It's when the sun is over at a 70, 80 degree angle to the surface, so really low down on the surface, that we're finally able to see, well, the boulders have long shadows, the crater walls stand out remarkably. So the different sun angles allows us to, on one hand, map the albedo, the color features, light versus dark soils. And the sun angle being low allows us to map where are all of the craters and boulders. Now, why exactly do boulders matter? I mean, they're a nuisance to farmers. Why are they such an awesome thing to asteroid mappers?
Well, they're great on Vesta because when you have boulders being thrown out of a crater, you get some kind of an idea about whether it's rock. So if a boulder is thrown out of the crater, it's more likely that there's rock underneath the crater. If you just get finer grain material like sand kind of size being thrown out, then you can be pretty sure that the crater was just formed in this regolith covering that's on Vesta, so just the kind of sandy, soily stuff that covers Vesta. But if you're throwing out boulders, it's likely that the regolith is thinner in that area because you excavated down to the solid rock, or possibly also that there just happened to be some rock in that area. So you can kind of do some vague subsurface mapping as well if you map where the boulders are.
So normally I don't give in to crazy people, but sometimes they write things that are so funny that you have to pay attention to them. Someone whose name I'm not going to give in to saying writes, is the government run by secret societies, and are they imposing aliens? I'm not sure how you impose aliens. So the reason I mention this is we were all at a meeting last week, not all of us, but many of us, you and I both were, Joe was there, Nicole, who's producing all of this, was there. We were at a meeting of the American Geophysical Union in San Francisco, and there's a bunch of climate change scientists there, and there's free beer every night. And Nicole made the great point that scientists can't keep secrets. We find cool stuff and we have to tell everyone. and you can't have a conspiracy theory because we can't keep our mouths shut. The Mars team made a noise of glee on the radio about how awesome the results coming back from Mars rover are, and everyone was like, no, you're not allowed to do that. But the truth is, we get to be some of the first people to see the surfaces of other asteroids, of other worlds, and we're so excited by what we do that well, you can tell us to keep our mouths shut, but we're going to tell our spouses, we're going to tell our friends. And
everybody tells one person who tells another one person.
yeah. So we can't keep secrets. And also, hurting us is like hurting cats. So trying to do a conspiracy, you can't get us all moving in one direction. So, yeah. So to go back to slightly more interesting science-y stuff. So here the question is, has Dawn turned around to take pictures of what Earth looks like? And also, secondary, do Lagrange points affect Dawn at all?
Well, as far as I know, Dawn has not turned around to look at the Earth yet. We did do a flyby of Mars back in 2009, I think it was. This was to get some help on the way to Vesta with a gravity assist from Mars, and some of the instruments were tested out at Mars. So I think that's the only other body that a picture has been taken of Vesta by the Dawn spacecraft. But I'm pretty sure the Earth would look very, very small from Vesta, so it probably wouldn't look terribly exciting.
No, that's true, and this brings up the issue of your spacecraft, our spacecraft, the everyone who paid taxes spacecraft, has one of the funkiest drives out in the solar system. Do you want to explain a little about how it's moving around? And I'm going to mark some more craters while you explain.
Sounds good. Yeah, so we've got an ion propulsion drive. So we have 3 different ion propulsion engines. So it means when you have 3, you can move in pretty much any direction that you want to move in. And basically what the spacecraft does is it shoots ions of xenon out the back. And then because you are in space, you're just free floating. So when you shoot something out the back, you move in the opposite direction. And this is a really great kind of propulsion because it's pretty light. It's very easy. You just shoot it at the back and it works perfectly. It is quite slow, however. The acceleration that we get from this is about the same as just putting a piece of paper on your hand. It's about the same force. But over time, this builds up and the spacecraft can move very, very large distances. And at the moment, we're using this ion propulsion to go to Ceres because we left Vesta a few months ago, and we'll be getting to Ceres in the early part of 2015.
And to try and explain what it means to have an ion drive, anytime you take an atom and you strip off a few of its electrons, it ends up as a charged particle. And if you've ever moved something around using magnets, well, moving things around with electric fields is very, very similar. So, in fact, you can use magnetic fields to move charged particles. It's the whole electromagnetic force stuff that you may have heard about in high school or studied in college that gets rather complicated. Now, when you use that electromagnetic field to move a charged particle, you can get it going significant fractions of the speed of light. And that means you have something very, very small going exceedingly fast. And that is able to very, very slowly get the spacecraft accelerated to also going very fast, which is kind of awesome. And I'm looking at an image that has, I just marked it as a crater chain, but I'm not sure if it's a crater chain or a boulder rolled down the side. This is one of those times. So the way Asteroid Mappers works is we get about 15 different people to look at every image. And if a bunch of people all mark an image as having either a weird feature or a specific feature, the scientists are going to go in and go, I wonder what's there. And then we also take all the combined results of all the people looking at these images. And if 3 or more people all mark the same crater, we consider it to be real. And so we build up validity through statistics. Now, one of the things that we're going to be working on adding in the future is actually the ability to periodically validate what you do in real time. We already have this up for moon mappers, and what this means is we'll ask someone like poor Jennifer, who we will have look at a whole bunch of images all in one go, so her head's in the same place the entire time she does it. And we'll ask her to look at all of these different images and mark all the stuff she sees in them. And when she's done, we'll take and give those images to the members of Asteroid Mappers on a regular basis and then tell them what fraction of the things she saw that they also saw. And if you don't match her results a lot, we either look at her results and go, no, Jennifer, you have to go back to what you were doing. Or we tell you, could you please retake the tutorial? Now, one of the interesting things that we learned with moon mappers is the people doing this in the public are actually more willing to mark every single item in the image than our poor innocent team scientists. And so this means that occasionally they're marking things that are real that our scientists simply got too tired to mark at the end of the day. Now, this is a really funky image where the crater in the upper left looks like it has black streakiness coming out of it, and it's somewhat misshapen. Can you explain what type of thing I'm looking at here?
Yeah, so the dark streaks, these are a good example of the dark material that we have on Vesta. We have a lot of dark material and also bright material. And in this case, this seems to be material that was thrown out of this crater as it was formed. So it's material that was ejected out of the crater. And it's possible that this material was either underneath the surface of Vesta and was then thrown out while the crater was being formed, or it could also have been the material that made up the little small asteroid that formed this crater and was then thrown out. It's kind of hard to tell either way. And then also you're mentioning that this crater has a strange shape. A lot of the craters on Vesta have this. You can see like the large crater in the bottom part of this image is kind of a weird shape as well. And a lot of these craters get these strange shapes just because sort of the mass movement of material, so little mini landslides, material just kind of cascades down and then causes the crater to have this kind of strange shape. So this is probably not how they were formed originally, but then in the millions and millions of years that they've been on the surface, they've just been changed by material cascading down towards the center of the crater.
Now, Vesta had what can best be described as a hard knock life. If you look at the small image that we have of Vesta up in the upper left-hand corner of this, and I'll work to try and zoom in on it, you can see that there's this belly button, outie belly button on, this is one of the poles of Vesta. Along with this, we see all sorts of wrinkle ridges, and it's a complex geometry that was unexpected. Can you explain what happened to this poor little rock?
Yeah, well, firstly, the bump that you were talking about down in the southern hemisphere, this is the central part of a very large crater that's been called Rea Sylvia. So when you get a very large crater forming, the end of this crater generally gets uplifted, so it creates kind of a little mini mountain, and this is called a central peak. So that's what's going on in this image here. This is the Rea Sylvia crater, and we were talking about the meteorites that came from Vesta earlier on, and it's possible that these meteorites were ejected off of Vesta as a part of this impact. So there would have been a relatively large asteroid that came in and formed this crater, and then material got shot out and then finally made its way to the Earth. And this impact probably had a very large effect on the rest of the surface of Vesta, because a lot of boulders and a lot of ejecta would have got shot all around the surface. And then it's possible that it also formed some of the linear features that we see, because when this impact came in, it would have made Vesta spin around kind of strangely while it was trying to get back to normal, and then this could have formed some of these linear features that we also see. And you can also form linear features by boulders kind of skipping or scouring across the surface that could also be formed from an impact.
Now, one of the awesome things about this mission is we get to see two different asteroids throughout the lifetime of Dawn. And Jason Wetzel asks, what are the risks, if any, that Dawn faces on its way to Ceres, being in the asteroid belt and all that?
Well, it's not actually as bad as you might think. The asteroid belt is very, very, very wide and very large. Just Vesta itself, it goes across the asteroid belt at great, great distances. Its distance from the sun changes. So the asteroid belt itself is very large, and you've got a reasonable amount of material within the asteroid belt, but not enough to completely fill it up. So there are an awful lot of gaps. And as far as I know, the route that the Dawn spacecraft is taking through the asteroid belt has been designed so that we go through some of these gaps. And so it's likely that we probably won't really encounter anything that could damage the spacecraft too much. Maybe just some smaller particles, but this is all kind of expected. So the risk is pretty low with traveling through the asteroid belt. It's not like in movies and stuff where they're dodging asteroids. They're very, very
So the Millennium Falcon would not have any risks going through our solar system's asteroid belt?
No, definitely not. They wouldn't have anywhere to hide either.
Oh no, quite sad. So here's another question. This one is from James Haney. Is there any indication that the asteroids are merely leftovers from the formation of multiple worlds, or if they're remains of a possible lost planet? So this is the notion that either worlds collided to create the asteroid belt, or perhaps one world failed to form, and if you scooped up all the asteroids, you could form a planet. Are any of these things that we hear and see in movies, is there any reality to them?
Yes, well, it's thought that the asteroid belt is formed in part by the gravity of Jupiter, which is beside it, kind of just messing around with all the material in the asteroid belt so that a planet couldn't form. It's also possible that just there weren't enough collisions or the right kind of collisions to stick all these asteroids together to form a larger planet. The Earth and all the other planets in the early solar system probably would have started out as a number of bodies that are kind of like Vesta that then collided together and stick together. So for whatever reason, Vesta and Ceres and the other large asteroids in the asteroid belt just never got the chance to form a planet.
And so they're only just a few % of the mass of all the other planets. This is not a lot of mass tied up in these little worlds. And I'm purposely training myself to use the word world instead of planet, asteroid, dwarf planet, or any of the other nomenclature, because, well, the definition for planet is currently a bit broken, since it requires planets to be orbiting the Earth's sun, which doesn't work so well for extrasolar planets. But there's also the issue that, well, everyone knows, not everyone, most people know Pluto used to be considered a planet, and it's now considered to be a dwarf planet. But it's not the only thing in our solar system to be demoted. Can you talk any about how Ceres also faced the loss of planethood?
Yeah, well, Ceres is also called a dwarf planet, as far as I'm aware. And I know that the Dawn team, we're all always going on about the fact that we have all these very diverse and interesting features on the surface of Vesta. So we often say that it has a lot of the complexity that you get in some other planets, but then you can't call it a planet. So I like the idea of using the word world. And then Ceres is slightly larger than Vesta, and it's also more of a sphere, so that's why it got a little bit closer to being a planet, but not quite. Didn't make it.
So does this mean that as we go through the images, we may find things like volcanoes, or just how complex is its geology?
Well, the volcano thing is interesting. A lot of people were expecting to find volcanoes on the surface of Vesta, but so far we haven't found anything that can be definitively categorized as being volcanic. And we think that this might be because Vesta is small, it only stayed hot and kind of molten or runny for a little while. So these features formed a very long time ago, and then all the material came in, forming craters, and basically just pummeled all of these volcanic features. But we do have an incredibly diverse range of craters. We have all this diverse bright and dark material, like we mentioned. We also have linear features, we have ridges, and we have long linear depressions called troughs. And then we have chains of craters, and then all of our regolith moving around forms very interesting features as well. So despite the fact that we don't have any volcanics, we have a lot of interesting stuff to look at.
And I just love the notion of a planet having a runny surface. That is perhaps one of the most fabulous things that I've heard described. And it's entirely true. Planets do periodically have runny surfaces. So what's your favorite thing that you've discovered so far looking over all of this?
Oh, I think probably just all of the diversity that we have all over Vesta. We've got so many interesting things, and just trying to figure out how they all relate to each other. So trying to figure out how the dark material relates to the bright material, and then how the large impact crater, the southern hemisphere, how that relates to other features on the rest of the surface. And what we want to do with the geological mapping is divide the surface up into a number of units and a number of features. And then once you have all those units and features, you put them into an order, so the oldest first and then working up to the youngest. So as a geologist, I really enjoy just figuring out all the connections between these different features to get a timeline for how the surface and then how Vesta itself evolved.
So we're starting to run up on the end of our planned time here, and I'm apparently still showing somebody's question. There we go. This has been truly fabulous, and for those of you who tuned into this late, this is a joint hangout posted as part of Google and Girl Start's December program. And I'm Dr. Pamela Gay. I'm on the faculty of Southern Illinois University, Edwardsville, and I run the CosmoQuest Citizen Science Project. And with me is Jennifer Scully, a graduate student at UCLA, where she works with Chris Russell, who's one of the lead scientists for the Dawn mission. Also with us is Joe Wise, who's one of the people who has helped work with us in many different ways to communicate out to all of you what's coming down from this spacecraft as it travels out amongst the asteroids. Our producer today is Nicole Galucci, and if you want to continue learning and being part of what we're doing, you can join us over at CosmoQuest.org, where we have we have images of Vesta waiting to be mapped by you. We have tens of thousands of images. Each one needs 15 pairs of eyes. When we make it past these images, we're going to have more images. When we're done with those images, well, we're going to have series to go through as well. So we're hoping that you will join us and you will become part of exploring our solar system through CosmoQuest.org and helping Jennifer and all of the rest of the scientists on our team use your data to understand our universe. So, Joe, do you have any parting words?
Yes, I wanted to certainly thank you, Pamela and Jennifer. Jennifer is actually in Ireland right now, so it's quite early for her. And so this has been just a really great time. We plan on doing this more often, periodically. We'd like for you to visit the Dawn webpage at dawn.jpl.nasa.gov. We have a little questionnaire there that we'd like for you to fill out that would really help us in planning more of these. We've got some interactives that we're going to be doing on the framing camera. We've got an interactive on the gamma ray and neutron detector that we're going to be hosting another Google Plus Hangout for this. For you who are educators, we're going to be doing some of these things about modules that we have. It was mentioned the CSI. We have a module on CSI that can be used in the classroom that focuses on some of the ways that the Dawn mission brings back information and interprets the information. And it's based on a CSI model. So we really are anticipating a great time of working with all of you. Stay in touch with our community either through CosmoQuest or through the Dawn Twitter and through our web pages. And we're very, very excited about having you be a part of our mission and the work that we do. So thank you again to all the team at McCrell, Scott, Jennifer, Pamela, everybody, and of course for all of you out there tuning in to us. This has been really great. We look forward to talking to you again soon.
And stay tuned for future Hangouts. I believe that our next event that's currently scheduled in December, we're slowing down during the holiday season here at CosmoQuest, but our next big event is going to be Sunday night's Virtual Star Party, which will be hosted by at Bald Astronomer Scott Lewis on Google+. And Nicole will be around, and starting in January, we're going to take the wonderful momentum built out of this December program and channel it into a whole new channel of content on YouTube. So stay tuned and check us out. We're Astrosphere Vids on YouTube, CosmoQuest.org online. Thank you again to Nicole, Jennifer, Joe. We have Whitney hiding off to the side. And thank you for all your help. And thank you out there in the audience for all the science that you learn and do every day. So have a good night, everyone.
Goodbye.
Thanks, everybody.
Bye.
Bye.